Isolated phase bus. Magnetic shielding. Introduction. The principle of magnetic shielding is used to limit the electromagnetic forces between the conductors in the adjacent phases of an isolated phase bus within safe limits during abnormal operating conditions. Prevent abnormal heating of structural steel in the vicinity. Contain the field intensity within health and safety norms. With the increase in the demand for power, as expected, the size of the unit generating set in a power station increased. An increase in the unit rating implied an increase in the rated current of the generator and consequent fault levels. A reliable and safe generator connections demanded, among several other requirements, withstand massive electrodynamic forces during fault, and contain the magnetic field within a confined area. Refer Figure 8.1. It was realized that the only way to meet the demand was to enclose each phase conductor in a separate conducting enclosure. Optimization has led to a tubular aluminium conductor supported concentrically inside a tubular aluminium enclosure and appropriately named as isolated phase bus. With the development in the aluminium welding technology, discontinuous type of isolated phase bus has made way for the continuous type isolated phase bus. A conductor carrying current will generate a magnetic field around it. Any metallic screen placed in the vicinity of a conductor carrying alternating current will induce a voltage. This voltage will drive eddy currents in a closed loop on the metallic screen. The induced eddy currents, in turn, will produce a magnetic field which will oppose the magnetic field produced by the conductor current. Consequently, the screen acts as a magnetic shield. This principle is used in isolated phase bus to contain the electromagnetic forces within safe limits. The degree of magnetic shielding can vary from a theoretical maximum of 100% in a continuous type isolated phase bus to a low of 20% in a discontinuous type isolated phase bus. Discontinuous or non-continuous type isolated phase bus. Refer Figure 8.2. In this type of isolated phase bus, the entire run of the bus is sectionalized into smaller convenient lengths. The length of the section is limited by the constraints of installation, and more importantly, by the voltage gradient along the section. The conductor is electrically continuous while the adjacent sections of the enclosure are connected by an insulating interface. Each section of the enclosure is earthed at one end. In this system, the current in one phase A induces a voltage on the enclosure of the adjacent phase B. The resulting eddy current produces a magnetic field that opposes the magnetic field generated by the current in conductor A. Consequently, the conductor in phase B experiences a diminished magnetic field due to the shielding by its enclosure. Discontinuous type isolated phase bus. Refer Figure 8.12. For the sake of convenience of analysis, consider a single-phase go and return conductor with their respective housings. Analyzing the current on the conductor and the direction of the consequent flux generated at locations C, D, E, and F, it is evident that in the annular space between the enclosure and conductor the field is opposed, while in the space between the enclosure outside, the field is reinforced. This implies that although the conductor is screened and shielded and therefore there is a reduction of forces acting on the conductor during short-circuit conditions, the enclosure is subjected to increased forces because of the increased field. Practically, the shielding factor can vary between 20% to 60%, depending upon the physical configuration such as diameters and thickness of the conductor and enclosure, phase spacing, length of individual section, etc. Continuous type isolated phase bus. Refer Figure 8.3. In this type of isolated phase bus, each of the phases of the entire length is sectionalized into smaller convenient lengths for transportation and ease of installation. The adjacent sections are welded to form a continuous enclosure from one end to another. The ends of the enclosure of each phase are shorted together. The entire enclosure configuration is then earthed at one end, preferably at the generator end. In this system, the current in one phase induces voltage along the length of its enclosure and a return path is available at either end. This circulating current, which is almost equal in magnitude and almost opposite in direction, produces a magnetic field that is almost equal and opposite to the one produced by the conductor. Consequently, the magnetic field outside the enclosure is minimal. This results in a very effective shielding. Continuous type isolated phase bus. Refer Figure 8.13. The enclosure currents are opposed to the conductor current and therefore, the field outside the enclosure is almost nullified. It implies that there will be a considerable reduction of the induced heating of any steelwork in the vicinity of the enclosure. For a perfect circular shape of conductor and enclosure of uniform thickness carrying current, the magnetic center of the conductor and enclosure will also be their geometric center, provided they are not subjected to any external magnetic field caused by current flowing in the neighborhood. Practically, the shielding factor can vary between 85% to 95%, depending upon the physical configuration, such as diameters and thickness of the conductor and enclosure. The field in the annular space between the conductor and enclosure will be the vectorial addition of the field generated by the conductor and enclosure. If the conductor is centrally placed with respect to the enclosure, the forces will nullify and the conductor will levitate at a point where the magnetic center of the enclosure and that of the conductor coincide. If the conductor is not in the center of the enclosure, the centralizing forces can be very severe during a short circuit. The conductor support arrangement should be designed to withstand these forces. If the conductor supporting arrangement facilitates the radial movement of the conductor around its geometric center, the forces on the insulators will be significantly reduced. Several manufacturers support the conductors inside the enclosure by a set of spring-loaded insulator to achieve this objective. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to Bala at busbarsystems.net.